Today we're going to learn how to find percent composition, which is a percentage of each element in a compound. The first one that we're going to look at is finding percent composition from mass. And so in lab, we were able to decompose a sample containing both iron and oxygen. And what we want to know is the percent composition, or the percentage of it made up of iron and the percent made up of oxygen by mass. In order to do this, the first step that we want to do is add up all the individual masses of each element. So in this case, there are only two elements, iron and oxygen. And if we add these two together, we get a mass of 150 grams. So that is our total mass. The second thing what we're going to do is find the percentage of iron in the sample. In order to find the percent iron, what we do is we take the mass of iron and we divide it by our total mass. After we divide it by our total mass, we're going to multiply it by 100 in order to get it into a percent. And when we go ahead and plug that in our calculator, we end up with a 70%. Now, we only have one other atom in the sample. We've got oxygen, so we're going to find the percentage of oxygen in the sample by mass. We have 45 grams of oxygen divided by our total mass of the entire sample of 150. Again, we multiply that value by 100 to get it to a percentage, and we get 30.0%. In order to check ourselves, it's always a good idea to look and make sure that all of your individual elements and the percentages from each of those add up to a total of 100%, which in this case they do. So we know that we did it right. All right, next example here, a little bit more work involved, but we're going to find the percent composition from a formula given. So in this example, we're trying to find the percent composition by mass in acetic acid. In order to do that, the very first thing that we need to do is calculate the molecular mass of the sample. Our molecular mass of the sample is going to be equal to 2. We have 2 atoms of carbon, so we're going to do 2 times the atomic mass of carbon off the periodic table, which is 12.011. And then we're going to add that to the atomic mass of hydrogen, and there are 4 atoms of hydrogen, so we're going to do 4 times the atomic mass of hydrogen, which is 1.0079. And then we'll add that to the mass of oxygen. So for oxygen, we've got 2 atoms of oxygen, so we'll do 2 times 15.9994. When we add all of those values up, we get a molecular mass of 60.0520 grams per mole. So this is the molecular mass of acetic acid. The next thing that we need to do is we need to figure out what the mass of carbon is over the total mass of the substance and multiply it by 100 to get our percent carbon. So we've already done a lot of the work here. We know that this portion of the molecule is made up of carbon by mass. This portion represents our hydrogen atoms, and then this portion represents the mass of our oxygen. So we can save ourselves a step here, and in order to find the percent composition of carbon, we can simply take 2 times 12.011 and divide that value by our total mass, 60.0520. We're going to multiply that value by 100 to get it into a percentage, and that comes out to 40.0%. To find our percentage of hydrogen within the compound, we are going to take the mass of hydrogen, 4 times 1.0079, and divide it by our total mass for the molecule. Multiply it by 100 to get it to be a percentage, and we end up with about 6.7%. And then our percentage for oxygen can be found by taking the mass of oxygen and dividing it by the total mass of the compound. This ends up about 53.3%. And in order to make sure that we did this right, we should verify that all three of these values add up to 100%, okay? Which they do, so we can know that we did that one right. Okay. Next, we're going to move on from percent composition, and we're going to look at something called empirical and molecular formulas. An empirical formula is the simplest whole number ratio that exists for a compound. An example of this in biology days is looking at carbohydrates. You learned that carbohydrates are always made up of the same elements, carbon, hydrogen, and oxygen atoms. And what you learned is that the simplest building block of a carbohydrate is what's called a monosaccharide. In an example of a monosaccharide, glucose, we know that the actual chemical formula for glucose is C6H12O6. We know the actual formula for a disaccharide like sucrose is about C11H22O12. And what we recognize is that if we take these values and we reduce them to their simplest whole number ratio, we always get about 1 carbon to 2 hydrogens to 1 oxygen. We would say this is the simplest whole number ratio for a carbohydrate. This is the empirical formula for a carb. Whereas the C6H12O6 would represent something called the molecular formula. The molecular formula is the actual number of atoms that you would find in that substance. So today we're going to learn how to find the empirical molecular formulas for a substance from data. So in example 1, we're going to figure out what the empirical formula is for a substance that contains both nitrogen and oxygen atoms, and we have the mass of each of those atoms. So in order to do that, what we need to do first is we have to convert the mass that we're given into moles. Once we have something in moles, then we can actually compare one atom to another. So step number 1, we'll go ahead and write the steps as well. We'll convert our mass data into moles. So starting with nitrogen, we've got 4.90 grams of nitrogen. And I know that 1 mole of nitrogen is equal to its atomic mass off the periodic table. So when we divide that out, we get about 0.350 moles of nitrogen. In the other sample here, we've got 11.2 grams of oxygen. And we're going to divide that mass by the molar mass of oxygen, which is 15.9994 grams. We get about 0.700 moles of oxygen here. So step number 1, we converted from mass to moles. The second step that we're going to do is we're going to divide all mole values by the smallest one. So I'm going to go ahead and add this down below. So if I take a look at my mole values, there's only 2 of them here, 0.350 moles of nitrogen and 0.700 moles of oxygen. Clearly, 0.350 moles of nitrogen is my smallest value. So what I'm going to do is divide 0.350 moles by itself, 0.305, and I get a value of 1. I'm going to do the same thing to my other sample. I've got 0.700 moles of oxygen. I'm going to divide it by the smallest mole value, and I get 2. Now these numbers here we're going to use in the next step. These numbers that I've circled, the 1 and the 2, are going to become the subscript on the molecule. This tells us the whole number ratio of the molecule. So this is, I'm going to write becomes the subscript on the molecule. In other words, this 1 from nitrogen tells us that in the empirical formula for this compound, there is 1 atom of nitrogen. And this 2 from oxygen tells us that there are 2 atoms of nitrogen. So this, NO2, is the empirical formula. It is the simplest whole number ratio that we can get for this substance. Now what we're going to do is look at another example. In this example, we are going to examine how to find the molecular formula for a compound. So we're looking at the actual whole number ratio that exists for a substance. So we're building off of the previous example. The question is, what is the molecular formula for the problem on the previous slide if the compound has a molecular mass of 92.0 grams per mole? So from the previous problem, we had found the empirical formula, which is NO2. So I'm just going to rewrite this here so we know what it is we're working with. The very first step in determining the molecular formula for a substance is to find the empirical formula mass. So again, I'll write the steps down for you. Step number 1, determine the empirical formula mass. We'll call that EFM to abbreviate. So our empirical formula mass taken from this formula above would be 1 atom of nitrogen times the mass of nitrogen off the periodic table plus 2 atoms of oxygen times the atomic mass of oxygen on the table. When we add that together, we get an empirical formula mass of 46.0055 grams per mole. So step number 1, we're just finding the empirical formula mass based on the empirical formula determined in an earlier step. The second thing that we're going to do is look at the given. The only given piece of information here is the molecular mass of the substance. So we know the molecular mass is 92.0 grams per mole. We know the only atoms that are in that sample are made up of nitrogen and oxygen, and we know that the ratio of those is a ratio of 1 nitrogen to 2 oxygen. So in the second step, what we do is we divide the molecular mass by the empirical formula mass. So in this example, we're going to take our 92.0 grams per mole, and we're going to divide it by 46.0055 grams per mole. When we divide that out, we get roughly 2. And in that third step, what we're going to do is take our empirical formula and we're going to multiply it by this whole number from the previous step. So we'll take our NO2 and we'll multiply it by this whole number ratio we got here, which is A2. So when we distribute this 2 across, we get N2O4. So the actual ratio, the molecular formula, is N2O4. This is dinitrogen tetroxide, which is one of the things that's used in rocket fuel. It's a powerful oxidizer. All right, let's move on to our next example. Our second example is going to be trying to combine both parts here. So we're going to look at what the empirical and molecular formula is for a substance that is made up of 59.96% carbon, 26.62% oxygen, and 13.42% hydrogen. And we're given the molecular mass of 180.2 grams per mole. So we're doing all of this together now. So the first thing that you need to recognize that's different is instead of getting a mass of our sample, we are instead getting percentages of each atom in the sample. So what we do as chemists to make this process a little bit easier is we make an assumption. We assume that we have a 100-gram sample. Because if I assume I have a 100-gram sample, it makes the math very simple. If I have 59.96% of carbon in a 100-gram sample, that would mean I have 59.96 grams of carbon. So we're going to make a little note here. We always assume that we're working with a 100-gram sample when we're given percentages and asked to find empirical and molecular formulas. So if I assume it's a 100-gram sample, then I can just directly go from the percent of carbon to grams of carbon. So I'm just going to do that in one step. This percentage now just becomes grams. So in this first step, I would take the percentage, convert it to grams, and then the next thing that we always do is go from mass to moles. I'm going to write some general steps on the side here, and we'll come back and review the steps at the end. But the first step is, if you're given a percentage, we always convert from the percent to mass. Again, making the assumption that it's a 100-gram sample. The second thing that we do is we take our mass and we convert it into moles, because we know when we have values in moles, we can compare them, different elements or different atoms in moles. And then our third step is we divide by the smallest number of moles. So we're going to just say divide by small. And then for the fourth one, only if necessary, you multiply until you get a whole number. And I'll show you this in a second example. So we're going to write it times until whole. And I'm writing it like this because then it kind of rhymes if you say it together. Percent to mass and mass to moles, divide by small, and times till whole. So if you say it like that, you can kind of memorize it pretty easily, and then you can think through the steps as you're going through an empirical and molecular formula. So our first step, we went from percent to mass. Now we're going to take the mass of each of these samples and convert it into moles. So 59.96 grams of carbon. I'm going to divide by the molar mass of carbon in order to get it into moles. All right, so I've got moles of carbon, 4.992 moles of carbon. For the next one, I know that 26.62% of oxygen in a 100-gram sample would be 26.62 grams of oxygen. And then I'm converting to moles by dividing by the molar mass. And we get 1.6638 moles. And then in the next step, we've got 13.42% of hydrogen, which is 13.42 grams of hydrogen in a 100-gram sample. 1 mole of hydrogen is equal to a mass of 1.0079 grams of hydrogen. And this comes out to be 13.3148 moles of hydrogen. So we did step number 1, percent to mass. Now we just did mass to moles. And then the third thing that we do is we divide by the smallest number of moles. So comparing my three numbers here, it looks like the smallest number is clearly the 1.6638. So I'm going to divide each of these mole values by the smallest number. All right, we pull out our calculator here, and 4.992 divided by 1.6638 is 3. This one is, of course, 1, and then this one is 8. Okay, so those come out to be about whole numbers here. Now, the next step that we do after dividing by small, occasionally we will encounter a situation where these numbers don't work out to be an even whole number. And so if they work out to be like 1.33 or 3.5, then we actually have to multiply all of these values by a number in order to get it to the nearest whole number. So I'll show you an example of that in a few minutes. But that's what this times until whole step is. We didn't need to do it on this particular problem. So now we take the three numbers that we got And this tells us the number of atoms of each element that we have in our sample, in our empirical formula. So the 3 means we have 3 atoms of carbon, the 1 means we have 1 atom of oxygen, and the 8 means we have 8 atoms of hydrogen. So for my empirical formula, I would write it out like this. I've got C3H8O. We typically write the carbons first, and then the carbons are what are going to be bonded to the other atoms, typically, in a molecule like this. So we typically write the carbons, keep them together, put the hydrogens together, and then oxygen together as well. Next step, we need to find what the molecular formula is. So if you recall from the previous example, in order to find the molecular formula, the first thing that we have to do is find the empirical formula mass. So now that I know what the empirical formula is, I can take this value and I can use it to find the mass. So we're going to take 3 times the mass of carbon plus 8 times the mass of hydrogen plus 1 times the mass of oxygen. We add all those values together and we get 60.0956 grams per mole. After finding the empirical formula mass, the next thing that we need to do is take the molecular mass that we were given. So here's one of our givens. And we take the molecular mass and divide it by the empirical formula mass. When we divide this out, we get approximately 3. This 3 is what we're going to use to multiply our empirical formula. So we do 3 times the empirical formula, or the simplest formula, and we're going to distribute the 3 to each atom. So 3 times 3 gives us 9, so there are going to be 9 atoms of carbon. 3 times the 8 for hydrogen gives us 24 hydrogens. And then 3 times the 1 oxygen gives us 3 atoms of oxygen. So C9H24O3 is the actual number of atoms in the sample, known as the molecular formula. All right, so that's all we were looking at for example 2. Now, in this next page here, this is the last part of the lecture, we want to show you some of the exceptions to empirical formulas. I mentioned before that if you get to the step where we're looking at the number of atoms in your sample, if you get a fraction of a number of atoms, that doesn't make sense. We know that atoms are not going to be in pieces and parts. We're going to have a whole number of atoms. So in order to get a whole number of atoms, if your whole number ratio, so looking at this previous problem here, if this did not end in a whole number, here, here, and here, then we would have to do this next step. So let's say that your whole number ratio ends in 0.5. So it could be 1.5, 3.5, doesn't matter. If one of them ends in 0.5, we're going to multiply all of the numbers by 2 in order to get it to our nearest whole number ratio. If your number, on the other hand, ends in 0.33 or 0.66, we would have to multiply everything by 3 in order to get the nearest whole number. And then if we have 0.25 or 0.75, we would multiply everything by 4. So let's try an example here. We're skipping a couple of steps. We're actually skipping the percent to mass part. We're skipping the mass to mole part. We're on the step here where you have your number of moles of atoms, and you're going to divide by the smallest number. So in this example, I'm going to rewrite it so I have space. I'm looking at 2.41 moles of carbon, 3.20 moles of hydrogen, and 2.39 moles of oxygen. The smallest value is the 2.39. So I'm going to take each of the other mole values and I'm going to divide them by my smallest number. So when I divide this one out, we get 1.008. Well, that's close enough to 1. We're just going to call that 1. The next one, 3.20 moles of hydrogen divided by 2.39. That gets me about 1.3389. Okay, well, that's not close enough to 1 to just call it 1. It's 1 and a little over a third. So this is going to be an example where I know I'm going to have to multiply it in order to get it to a whole number. Let's keep going with our last one. We have 2.39 moles of oxygen. We're going to divide it by itself, since it's the smallest value, and we get exactly 1. So taking a look at our values, again, it doesn't make sense to have 1 1/3 atoms of hydrogen for every 1 atom of carbon and 1 atom of oxygen. So what we need to do is we need to multiply this value by 3, and if we multiply that value by 3, we can get to the nearest whole number, which would be 4. Be approximately 4 here. So whatever I do to this step, I have to also do to the others. So we're going to multiply this by 3, that becomes 3. Multiply this one by 3, and we get 3 again. Now I could actually look at my empirical formula and say, for every 3 atoms of carbon, there will be 4 atoms of hydrogen and 3 atoms of oxygen. And so this would be my empirical formula for that problem.